Hey there and welcome. Ever wonder about the geometry that's kind of hidden inside every curve you see? Well, today we're going to pull back the curtain. We'll be looking at two really simple lines, the tangent and the normal, and see how they unlock a curve's secrets, all with the power of calculus. So let's get into it.
So let's start with this idea. What happens when a line just kisses a curve? Imagine a perfectly straight line just grazing a curve, touching it at one single tiny spot without ever crossing it. That line, believe it or not, tells us the exact direction the curve is heading in that one precise moment. And that's the core idea we're going to unpack today.
So here's the game plan. We'll kick things off with that intuitive idea of the touching line. Then we'll see how calculus gives us the exact tools to measure it. After that, we're going to build the actual equations for tangents and their partners, the normals. Then, for the fun part, we'll see what happens when curves intersect. And we'll wrap it all up with a handy little cheat sheet of the most important formulas.
All right, first up, the line that touches. Let's make sure we get a really solid, intuitive feel for this idea before we get into the math.
Okay, so what is a tangent line officially? It's not just any line that happens to hit a curve. It's special. It touches the curve at just one point in that little neighborhood, and, this is the crucial part, it has the exact same steepness as the curve at that one point of contact.
And this right here is probably the best way to think about it. Imagine you're driving along a sharp curve, and your tires suddenly lose their grip. The car's going to fly off in a straight line, right? Well, that line is the tangent. It perfectly captures your direction and momentum at the exact instant you started to skid.
Okay, on to section 2. Calculus finds the slope. So we get what a tangent is now, but how do we actually find its steepness? For that, we need to bring in the big guns, calculus.
Well, the magic key we get from calculus is something called the derivative, which we write as dy over dx. You can think of it as a slope-finding machine. You feed it the equation for your curve, and it gives you back a brand new formula, one that's built for one purpose, to tell you the slope at any point you want along that curve. It is an incredibly powerful idea.
So here's how it works. To find the slope of the tangent, which we call m, you just have two steps. First, find the derivative of your curve, dy dx. Second, plug the x-coordinate of the point you care about, x1, into that derivative. The number that pops out, that's your slope. Simple as that.
Okay, let's move on to section 3, building tangents and normals. Now that we know how to get the slope, we can build the full equation for the tangent line, and we can also build the equation for its perpendicular partner, the normal line, which, as we'll see, is super important in fields from physics all the way to computer graphics. It really boils down to a super simple 3-step recipe. Step 1, differentiate your curves equation to get that slope machine, dy by dx. Step 2, plug in the coordinates of your specific point to get a number for the slope, m. And finally, step 3, use that slope and that point to build the line's equation.
And this right here is the final piece of the puzzle. You probably remember this from algebra. It's the point-slope formula. Once you have your point x1 and y1 and you've calculated your slope, m, you just drop them into this template and boom, you have the equation for your tangent line.
Okay, so for every tangent line, there's a partner, the normal line. It goes through the exact same point, but it's pointed at a perfect 90-degree angle to the tangent. And this isn't just some geometric party trick. In physics, the normal represents the direction of a force, like gravity keeping a planet in orbit. In computer graphics, it's essential for calculating how light bounces off a surface to make things look real.
And the best part? The relationship between their slopes is just so simple and elegant. If your tangent slope is m, the normal slope is just -1 divided by m. We call it the negative reciprocal. It means if you've got one, you've pretty much already found the other.
So let's put them side by side. It's really clear. The tangent shows you the direction of motion along the curve. The normal points in a direction that's perfectly perpendicular to that motion. They are two sides of the same coin, describing the geometry at that single point.
All right, section 4. Now this is where things get really cool. We can take everything we've learned and use it to figure out exactly what's happening when two different curves crash into each other.
So think about it. When two curves cross, they meet at an angle. But how on earth do you measure the angle between two, well, curves? The answer is, you don't. What you do is you measure the angle between their tangent lines at that exact point of intersection. The tangents give us the nice, straight lines we need to make a measurement.
So how do we actually calculate that angle? We use this formula right here. All you need are the two slopes of the two tangents, m1 and m2, right at that intersection point.
You plug them in, and this formula gives you the tangent of the angle theta. It makes sense, right? Slopes are all about rise over run, which is the whole idea of tangent in trigonometry. From there, it's just a quick calculation to find the angle itself.
Now, that brings up a really neat special case. What if the curves don't just cross, but they meet at a perfect right angle? Is there maybe a simpler way to check for that?
Oh, you bet there is. And it is so simple. We call it an orthogonal intersection. If you take the two tangent slopes, m1 and m2, and multiply them together, and the answer is exactly -1, that's it. You've proven they meet at a perfect 90-degree angle. It's an incredibly fast and powerful test.
Let's actually walk through a real example to see this in action. We've got two curves here. For the first one, we find its slope, m1, is -y over x. For the second curve, its slope, m2, is x over y. Now, for the test, we multiply them. The -y on top cancels the y on the bottom, and the x on the bottom cancels the x on top, leaving us with just -1. Since the product is -1, we know for a fact these two curves are orthogonal. And that brings us to our final section, a calculus cheat sheet. Let's just pull everything together and look at some of the shortcuts that come out of all this.
See, because these kinds of calculations are so fundamental for common shapes like circles or parabolas, mathematicians have already created pre-solved formulas. So instead of having to find the derivative every single time for a circle, there's a direct formula you can use. You can think of them as expert-level shortcuts that let you skip a few steps.
So to recap our whole journey, here are the four big ideas. The slope of any tangent comes from the derivative, dy dx. The slope of the normal is just its negative reciprocal, -1 over m. The angle between curves, you find that using the slopes of their tangents. And for that perfect 90-degree intersection, all you have to do is check if the product of their slopes is -1.
And that's a wrap. We've seen that with just a little bit of calculus, you can unlock this incredible ability to describe the precise direction of a curve and even how different curves interact. So the big question I want to leave you with is this: where are you going to see this hidden geometry now? In the path of a basketball shot? The design of a roller coaster? The way two roads merge? The geometry, it turns out, is absolutely everywhere.